Newton's law of cooling states that the rate at which an object cools or heats up is proportional to the temperature difference between the object and the surrounding temperature. Before we get anywhere with this, I'm going to say in terms of variables, uppercase T often refers to temperature. Lowercase t often refers to time. So please do not mix up the cases there. Let's unpack this a little bit. The rate at which an object cools is proportional to the temperature difference between the object and the surrounding temperature. We saw something like this in a previous example. The rate. Now we're talking about the rate at which an object cools or heats up. So d uppercase T, d lowercase t, that is d temperature, d time, is equal to a constant of proportionality, K, times the temperature difference. That temperature difference, we're going to express it as T minus T sub S, where T is the variable temperature and T sub S is the surrounding temperature. If we're talking about a pie that's being taken out of the oven, then T, the temperature, is the temperature of the pie as it cools. The surrounding temperature would be the temperature of the kitchen in which the pie is sitting. K is the rate of temperature change. Correction, it is the relative rate of temperature change, because the actual rate of temperature change is dt dt. Now this is a similar situation to the population model that we saw. And what we're going to do is we're going to put variables on together. So we'll write this as dt, that's uppercase T, divided by T minus T sub S, the surrounding temperature, is equal to K dt, that second T being time. And we'll deal with this the way we dealt with the last one. We're going to integrate. And so on the left-hand side, we have the natural log of the absolute value of T minus T sub S. And that's equal to the right-hand side, which is KT plus C. We have our variable of interest T in a natural log, and so we are going to exponentiate both sides. We're going to be a little careful though. Absolute value of T minus T sub S is equal to e to the C times e to the KT, where the sum and the exponent becomes a product of e to the C and e to the KT. The careful part is I'm keeping the absolute values. You see, if T minus T sub S is positive, then we have a cooling situation. That means that the object that's cooling has a higher temperature than the surrounding temperature, and so it'll decrease. But if T minus T sub S is negative, then the surrounding temperature is greater than the object's temperature, and we have a heating situation. This would be like you take a pie out of the oven, or excuse me, the refrigerator, and set it on the counter. And at this stage, the absolute values are required because I have a product. Well, we really had e to the KT plus C a moment ago, and that can't be negative. Now I'm going to avoid the entanglements of an absolute value equation and say that we end up with temperature as a function of time. So T of T is equal to T sub S plus d sub 0 e to the KT, where d sub 0 is the initial temperature difference. And the sign of d sub 0 will be positive or negative depending on what situation we have. I'm going to put that equation into a box, and then we're going to look at a visual. Suppose we have a horizontal time axis, lowercase t, a vertical temperature axis, uppercase T. I'm going to draw a horizontal line here at a mark which would be the surrounding temperature, T sub S. And assuming a positive initial temperature difference, our law of cooling is actually going to give us a decay graph. And what we see here is the initial temperature difference is, well, at the initial time t equals 0, you have the greatest temperature difference. And at that time, you have the greatest rate of temperature change. As the object cools and its temperature becomes closer to the surrounding temperature, the rate at which it is cooling levels off and eventually becomes asymptotic with the temperature of the room. So this is a great picture to show that the rate at which the temperature is changing depends on the difference between the two temperatures. This is what is meant by a constant relative change in temperature. And because this is a picture of decay, that will mean that K is negative. This picture goes along with the case that D sub 0 is positive. What if it's negative? So let's suppose that our initial temperature difference is negative. So D sub 0 is negative down here. Tried to cram that in there. I'm not sure if it worked. Anyway, then it will still become asymptotic with the room temperature. It will be cooling, but because D is negative, that would actually flip the exponential part of the graph upside down. It would be a reflection. But it would be a reflection of something that still had a negative K.